Have you ever looked up at the night sky and wondered just how far the universe extends? Today, we're embarking on an extraordinary journey through cosmic scales that will challenge everything you thought you knew about distance and time. We'll explore the incredible limits of space by examining some of the largest structures in the cosmos, from our local galactic neighborhood to superclusters spanning billions of light years. Along the way, we'll discover massive cosmic webs that connect the universe and peer into one of the deepest views of the universe ever captured, revealing secrets about the cosmos that existed long before our world came into being. Let's start with something familiar. Our home galaxy, the Milky Way, isn't floating alone in the void. It's actually part of a small cosmic neighborhood called the Local Group, which contains about 50 galaxies, including our nearest major neighbor, Andromeda, located about 2.5 million light years away. Now, it might seem obvious to us today that these are separate galaxies, but this wasn't always known. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery that forever changed our understanding of the universe. By observing variable stars in what we now call Andromeda, he proved that it wasn't just a nebula within our own galaxy, but an entirely separate galaxy millions of light years away. This revelation expanded our cosmic perspective dramatically, showing us that the Milky Way was just one of countless galaxies in a much larger universe. This neighborhood also includes smaller satellite galaxies like the Large and Small Magellanic Clouds, which orbit the Milky Way like cosmic companions. But these relationships aren't peaceful. Powerful tidal forces constantly pull at these galaxies, stretching and distorting them as they interact. In fact, the Milky Way and Andromeda are on a collision course, destined to merge in about 4.5 billion years, creating a new elliptical galaxy. These gravitational interactions aren't just dramatic events. They're fundamental to how galaxies evolve, triggering bursts of star formation and reshaping galactic structures. The Local Group is just the beginning, though. Galaxies throughout the universe tend to cluster together due to gravity, forming groups and clusters that can contain hundreds or even thousands of galaxies bound together by immense gravitational forces. Now imagine looking out into space and seeing galaxy clusters that are 8.8 billion light years away. That's not just a measure of distance, it's also a measure of time. Light travels at about 186,000 miles per second, but even at that incredible speed, it takes billions of years to reach us from these distant objects. This means the light we're seeing today left those galaxies 8.8 billion years ago, long before our Earth even formed 4.5 billion years ago. We're literally looking back in time. These massive galaxy clusters are some of the most fascinating objects in the universe. Back in the 1930s, Swiss astronomer Fritz Zwicky was studying one particular cluster, the Coma cluster, when he noticed something puzzling. The galaxies in this cluster were moving far too fast to be held together by the gravity of the visible matter alone. They should have flown apart, but they didn't. Zwicky realized there had to be some invisible mass holding everything together, something he called dark matter. He also pioneered the study of gravitational lensing, observing how these massive clusters bend and distort the light from even more distant galaxies behind them. This phenomenon acts like a cosmic magnifying glass, and Zwicky's observations were among the first hints that the universe contained far more matter than we could see. Between the galaxies in these clusters lies an incredibly hot intracluster medium, a thin gas heated to tens of millions of degrees that glows brightly in X-rays. Within these clusters, galaxies don't just sit peacefully, they frequently collide and merge with one another, creating spectacular cosmic interactions that reshape their structures and trigger intense bursts of star formation. These clusters don't exist in isolation either. They're connected by vast filaments of galaxies forming superclusters, the largest known structures in the universe. Our understanding of these massive structures took a revolutionary leap in the 1980s when astronomers Margaret Geller and John Huchra began systematically mapping the positions of thousands of galaxies. Their groundbreaking work revealed something nobody expected. Galaxies weren't randomly scattered through space, but organized into an intricate cosmic web of filaments and voids. This discovery completely transformed how we view the universe's structure. What holds these enormous structures together? Dark matter, the mysterious invisible substance that makes up about 85% of all matter in the universe, provides the gravitational scaffolding that binds superclusters. The story of dark matter actually begins much earlier, with Fritz Zwicky's pioneering work in the 1930s on the Coma cluster, where he noticed galaxies moving far too fast to be held together by visible matter alone. Decades later, Vera Rubin confirmed dark matter's existence through her meticulous observations of galaxy rotation curves, showing that galaxies spin in ways that only make sense if they're embedded in massive halos of invisible matter. These cosmic filaments, made of both visible galaxies and dark matter, stretch across hundreds of millions of light years, creating a foam-like pattern throughout space that we call the cosmic web. This web isn't random. It contains fossil imprints from the early universe called baryon acoustic oscillations, subtle patterns in how galaxies are distributed that echo sound waves from when the cosmos was just 380,000 years old. But there's another force at play. Dark energy, the mysterious force causing the universe's expansion to accelerate, is constantly stretching these structures and influencing how the cosmic web evolves over time. One of the most profound demonstrations of this cosmic scale is the Hubble Ultra Deep Field, an image captured by the Hubble Space Telescope. The story behind this image is remarkable. Back in the 1920s, Edwin Hubble revolutionized astronomy by proving that the universe extends far beyond our Milky Way and that it's actually expanding. His legacy lives on in the Space Telescope named after him, launched in 1990, which has given us unprecedented views of the cosmos. The ultra-deep field itself represents an extraordinary achievement by the telescope's team, who pointed Hubble at a tiny patch of seemingly empty sky, no bigger than a grain of sand held at arm's length, and captured light for over 11 days. What they found was astonishing: nearly 10,000 galaxies, each containing billions of stars. This image reveals something remarkable about the universe: redshift. As the universe expands, light from distant galaxies stretches to longer, redder wavelengths, and by measuring this redshift, we can determine how far away these galaxies are and how long ago their light was emitted. The ultra-deep field shows us galaxy evolution across cosmic time, revealing how galaxies looked when the universe was just a fraction of its current age, from mature spiral galaxies to irregular, chaotic proto-galaxies still forming their first stars. Behind all of this lies the cosmic microwave background, the faint afterglow of the Big Bang itself, providing a backdrop to all the structures we observe. So the next time you gaze at the stars, remember that you're not just looking out into space, you're looking back through time itself. This is the concept of look-back time, made possible by the finite speed of light. The foundation for understanding this was laid way back in 1676 when Danish astronomer Ole Rømer made the first measurement of light's speed by observing the moons of Jupiter. His discovery that light travels at a finite speed, rather than instantaneously, was revolutionary. From this insight, the concept of look-back time gradually developed as astronomers realized that the time light takes to travel means we're always seeing the universe as it was in the past, not as it is now. Because light takes time to travel across the vast distances of space, observing distant objects is like opening a window into the past. When we look at galaxies billions of light years away, we're witnessing the universe as it was in its youth, seeing the early stages of cosmic history when the first galaxies were forming, stars were being born at prodigious rates, and the universe looked dramatically different than it does today. We're not just observers of the present cosmos. We're witnesses to billions of years of cosmic evolution, watching the universe as it was billions of years ago, when our own world didn't yet exist.